Welcome everyone to this new Asterisk webinar. As you know, you probably know if you're following these webinars, we're organizing a series of webinars under the umbrella of the Asterisk project, which is trying to convert seawater into green hydrogen. This project is funded by the Clean Hydrogen Partnership and the European Union. And it's got a really fun thing is that we weren't the only ones funded through this call for seawater electrolysis. There were actually 3 other projects funded through the same call with the same pot of money from the Clean Hydrogen Partnership. And what we're doing here at Asterisk is invite each of the other projects to this webinar series so they can present their projects, they can present the preliminary results. And today it's a great pleasure for me to introduce SWEETHY, which is another project in the same call as Asterisk, also funded by the Clean Hydrogen Partnership and the European Union. And also working on an ion exchange membranes, but we'll hear more about that later. 2% SWEETHY, we've got Olesia Danyliv, who is a researcher in hydrogen technologies at the Research Institute of Sweden, RISE, and also the project coordinator for SWEETHY. She's got a background in materials and mechanics and civil engineering, but also electrochemistry and a lot of different battery related technology, green hydrogen, and robust energy systems. So it's a real pleasure to have Olesia with us here today. And I think she wants to tell you more about SWEETHY. So I'm going to shut up about the project and leave the floor to Olesia. I'm really looking forward to your presentation and to learning the differences between Asterisk and SWEETHY. And at the end, we'll have a short Q&A with Olesia and myself. If you have any questions during the video, please use the YouTube chat function to send the questions directly into the chat. And hopefully we'll monitor them at the end of the presentation and bring them up to Olesia for responding and having a fruitful debate at the end of the presentation. Without further ado, it's a pleasure for me to introduce Olesia Danyliv. Again, the floor is all yours.
Thank you very much for this kind introduction and for introduction of our project, which is a very challenging project about direct seawater electrolysis technology for distributed hydrogen production. And before I will tell you how we process seawater with the innovative anion exchange membrane water electrolysis technology to produce green hydrogen, I would like to pinpoint that you are very welcome to go to our website, which is constantly updated, SWEETHY.eu. There you will find a majority of information that I will present today. Another option, a very good option, is to subscribe to our newsletter, because then you don't need to go to website from time to time, but you will get the updates to your email about all what is happening in SWEETHY. And the third thing, if you have any questions about the project, any ideas that you would like to collaborate, please feel free to contact me by this email that you see at the screen or our communication team at Uni Research. Another small announcement before I go deep in the explanation of SWEETHY, I would like to tell you that we are organizing together with 4 other projects dealing with electrolysis technology, which are Protis, Unicorn, Animal, and Push. The event that is called the European Symposium on Durability Issues in Low Temperature Water Electrolysis, Marcus Wallenberg Symposium. It will be happening in Stockholm on 13th to 15th of October this year. The symposium is organized by 5 organizations, which is RISE that I'm representing today, but also the French Corrosion Institute, which is our partner in SWEETHY. Then the Royal Institute, Technological Institute in Stockholm, KTH, the University of Galway in Ireland, and SINTEF, the research institution in Norway. These 2.5 days of event will be full of nice discussions about durability issues in electrolysis, with oral presentations, and very important with a poster session, which will be given a lot of attention. So even though the abstract submission is closed, but if you are interested to participate, the registration will be open very soon, and the early bird registration will be quite fast. So if you have some questions and would like to join this event, you are welcome to contact me or the symposium email that you see here. But of course, all this information is also on the SWEETHY website. So very welcome to take to consideration this announcement and to participate in this event. And now, after announcing the important details, and now we go deep into description of the SWEETHY project. So as Fernando mentioned, this project was financed within the same program as 3 other projects about seawater electrolysis. SWEETHY project is a 4-year-long project. It started in March last year, and it will finish in February 2029. So we are now in the months 15 of the project. The budget of the project is approximately 4 million euros, and it is divided between 9 partners throughout 7 European countries. And since this project is a lot about collaboration, of course, so I would like to pay attention to each and every partner in this consortium. And the first in the list is the National Research Council of Italy, CNR-ITAE. I will tell you what are the main activities of these partners in the SWEETHY project. So CNR-ITAE is responsible for catalyst development, characterization, and validation. And also another main activity of CNR in the SWEETHY project is to validate the final SWEETHY prototype of the anion exchange membrane electrolysis stack, implemented with a balancer plant, and test and validate the materials that are being developed in the project. All this validation of the final prototype will happen with the seawater taken from the coast of Sicily, because CNR is situated in Sicily, in Italy. The next partner is the German small-medium enterprise Senmat, who is responsible in SWEETHY for the development of ionomer materials, and these are ionomer binder and membrane, anion exchange membrane. The next partner is the German Aerospace Center, DLR. This partner will be responsible for development and testing of the membrane electron assembly in the single cell. They are also doing the development of anti-corrosion coatings of the metal components inside the cell. And the next partner is from Spain, and it's CIDATEC Research Organization. It's another partner who is doing the catalyst development, characterization, and validation. They are also focusing on characterization of corrosion behavior of bipolar plates and porous transport layers in the SWEETHY cell and stack. The partner from France is the French Corrosion Institute, and as the name says, they will be focusing on corrosion activities. So they will be testing metallic components both inside the cell and in the balance of plants for the corrosion behavior. Another German small-medium enterprise proposed they are supporting the whole project with the development of electrolysis hardware, both the single cell and also the intermediate stack and the final SWEETHY stack prototype, which is a 10-cell stack. Moreover, they are the main drivers for harmonization of the testing protocols on the single cell level between the partners that are having their hardware at their laboratories. Then we are coming to the research institution RISE, which I'm representing in Sweden. Apart from being a project coordinator, we are also involved in single cell testing, but we are looking mostly not on the materials, but on the testing conditions, which electrolyte feed needs to be given to the single cell, how it influences the performance of the cell. And also we are working towards a simulation of intermediate conditions of operation. Another big activity within the project, we will be testing the intermediate prototype, which is a 5-cell prototype. And there we will look at the performance of the developed materials. And another type of activity within this project, which RISE is involved into, is the sustainability and techno-economic assessments. SINTEF, the next partner in this consortium, which is a research organization in Norway, will be also focusing on the technological part, which is the development of self-standing catalysts with a novel architecture, and less technological direction, which is sustainability analysis, which includes industrial symbiosis, integration of the SWEETHY Project whole energy system, different environmental, social LCS, and techno-economic assessment. And the last partner in this list, but a very reliable partner that we are having great support with dissemination, communication, exploitation activities, is Uni Research, which is a grants and innovation consultancy from the Netherlands. So before telling you what are the main objectives of our project, we need to understand what are the challenges. Of course, I cannot tell you in this short time all the challenges, but I try to specify the two main that are very well reproduced towards what we're doing in the project. Of course, the main challenge is that the electrolyzer is fed with seawater. What does it mean? It means that we will, of course, have high degradation rate of components and materials in the cell and stack, in the balance of plant. We will have high potential for corrosion of metallic components. We will have physical blockages because of solid impurities, because of microbial contamination. We will also have a competition on the anode between oxygen evolution reaction and chloride chemistry. We'll have broad pH fluctuations during the hydrogen evolution and oxygen evolution reactions. Another big challenge, but it's more on the industrial level, it's okay, we have a new technology, seawater electrolysis. How can we then take it outside the lab? And that's how we are looking into how it is possible in terms of cost, sustainability, interplay, acceptance of this new technology to implement the seawater electrolysis in reality, in real life. And that's how we come up to the main objectives of our project. The first one is specified is that we will develop the materials and components in the SWEETHY prototype that will be able to withstand seawater conditions. And of course, when we have the objective, we are trying to define the key performance indicator for our project. And they are defined here, as you see in the slide, that for direct seawater operation, we are working towards electrodes with the reduced overpotential, towards catalyst with the as low as possible degradation rate, towards anion exchange membrane that has high conductivity, and towards metallic cell components that have low interfacial contact resistance. Another objective is that we will develop and test a short and scalable half-kilowatt stack, ion exchange membrane stack. And for that, we define the key performance indicator that we will need to validate the developed materials in the stack during more than 2,000 hours with direct seawater that has high salinity, more than 35 grams per liter of salts. Then we also need to validate it with dynamic operation, because we are looking how to work it with intermittent conditions coupled to renewable sources of energy. And of course, we have not only the project-related KPIs, but also the KPIs that were defined with the strategic research and innovation agenda. And we need to have a stack that has reduced energy consumption, which you see at the screen. But of course, this last will be validated by the end of the last three KPIs. They will be mostly validated by the end of this project. The third objective is that we need to find the industrial partners that are capable of reusing byproducts from the electrolyzer plant, because we need to find symbiosis between the different industries to make the seawater electrolysis interesting technology for usage in real life. So within this objective, we'll develop and evaluate 2 case studies of usage of the SWEETHY system in reality. And of course, all the use cases, they are related to the cost of produced hydrogen. So the objective of our project is to reach the levelized cost of hydrogen of less than 8 euros per kilo. The last fourth objective of this project is to minimize environmental impact of the electrolyzer. For this, we are doing the life cycle assessment, where we will try to, together with the iteration with the technological partners, development technological part of the project, to reach the SWEETHY system with a footprint less than 2 kilos of CO2 per kilogram of produced hydrogen. And of course, we need to work towards integration of the system to have the minimum use of local resources and energy. So how are we going to reach all these objectives, key performance indicators, and everything that we have a goal by the end of the project? We can define 3 main approaches that I'm going to go through right now. The first one is focus on the cell level, where we'll do the material development. Then we go further to the cell and stack level, and we are focusing on electrolyzer configuration, and then to implement the whole system in the huge energy and industrial system, we are looking at the sustainability analysis. And how exactly are we going to do that? Well, the requirement of the call for this project was to go from TRL 2 to 4. So that's why we will have now 2 boxes, one when we are looking at the TRL 2 to 3, and another one TRL 3 to 4. So when we are starting with the low TRL 2, on the material development approach, we will be working towards development of platinum group metal-free, selective and durable electrocatalysts, on the ion exchange membrane of high ionic selectivity and anti-fouling properties. And we will develop anti-corrosion coatings for the metallic parts of the cell, bipolar plates and porous transport layers. Then when we'll go to the approach for electrolyzer configuration, we are looking on optimizing the single cell testing conditions so that all the partners are doing the single cell testing with the same conditions. We are also stepping from the single cell level checking of our newly developed materials to the intermediate stack, which is a 5-cell stack. We will also analyze byproducts during all this operation on the cell level and on the short stack level. When we move to the sustainability approach, we will be starting with performance screening activities, where we interview stakeholders and do the initial life cycle assessment. And we also map the potential industrial systems, integration, and symbiosis between SWEETHY system and the other systems. Then when we're trying to high up the tier level, on the material development level, we are looking on scaling up of all the materials so that they could fit to the final prototype of SWEETHY, which is a 10-cell IMV stack prototype. On the electrolyzer configuration level, we are designing this final prototype. We are designing the balance of plant that can withstand the seawater operation, and we integrate the final prototype with the balance of plant, and we secure that we can test the developed materials during more than 2,000 hours. And on the sustainability analysis level, we will perform the full LCA, which includes also the social and environmental LCA, according to some ISO standards that you can read from the slide. And we'll also perform the techno-economic assessment regarding the 2 case studies. Now I will specify even more what is happening, what has happened, and what will happen within these approaches that you have now seen in the previous slide. So within material development catalysts, we are working towards development of platinum group-free cathode and anode electrocatalysts. 3 main partners are involved in this work: CNR, CEDATEC, and SINTEF. These are the PGM-free catalysts that were chosen for this project. On the cathode level, it's nickel and molybdenum carbon catalyst made by spray coating, nickel and molybdenum sulfur alloys made by electrodeposition method, and nano-PTLs with nickel and brass nanowires. For the anode catalysts, we also test the last 2 catalysts that I mentioned, but we also synthesize the nickel and iron and nickel and manganese laid double hydroxide. We also chose the benchmark materials, platinum for cathode and cobalt oxide for anode. So up to now, we can report that all the synthesis of all these catalysts that I presented are completed. The information can be found in the public deliverable D31, which can be easily accessed via our website. The synthesis was done following 2 approaches, chemical and electrochemical, which helps us doing the multivariable optimization, which means that we explore broader design space for the catalyst and electrodes operating in seawater environment. From then we also can report that the deliverable 3.2, which describes the screening of all these materials in a half cell, is also a public deliverable that you can read through. And the scale up of all these materials is ongoing. From the images in this slide and in the next slide, you can maybe quickly see that we succeeded in synthesizing nice materials with different, they are homogeneous, reproducible, they are highly porous, and they show good performance. Even though for cathode materials, when replacing fully platinum with PGM-free materials, it's still hard to reach the same performance as the platinum. But nevertheless, the SWEETHY electrocatalyst that developed cathode material, they show promising performance and they are good alternatives that need to be tested further on in a single cell. Regarding the anode materials, we can also say that materials with nice performance were achieved. They also reached the performance of the benchmark materials. But more in details, I invite you to read the deliverables because it's impossible to go through all the materials and all characterization in the presentation. What we're doing now on catalyst development is that we're screening this catalyst in a single cell. And this is the topic for the upcoming 2 deliverables, D33 and D34, which will be also public and will be published in summer this year at our website. I cannot show you much more than this, but we are doing the durability test, and what we received up to now that the developed catalysts, they show good durability during 1,000 hours, and the degradation rate was not more than 13%, which lies very good in the KPA that we defined in the beginning of the project. So this gives us promising results for the developed PGM-free materials for seawater application. In the upcoming deliverables, you will also see not only performance, but also how the catalyst needs to be conditioned prior to durability tests, and also how the configuration of a single cell looks like, because we are exploring also different filtering of solid particles inside the cell that are being formed during the seawater electrolysis operation. The next part of material development is the polymer part, and SENMAT and CNR are involved in this development. For SWEETHY Project, we are using the commercial membrane from SENMAT, which is called Iron Flex membrane, and it is being optimized for the seawater electrolysis application. We are increasing its hydroxide selectivity and increasing its antifouling resistance. Moreover, the work on iron development based on the similar polymer is ongoing, and more results will be also presented by the end of this year. To finish describing the material development within SWEETHY, I refer to the anti-corrosion coatings that we are doing in the project. So within development of anti-corrosion coatings, we are looking at the corrosion behavior of uncoated and coated bipolar plates and porous transport layers. We are developing the novel anti-corrosion coatings. We are assessing the risk of galvanic corrosion in confined areas, and we are also looking at the corrosion resistance of pipe materials. So far, the material that can be found in 10 days time at 10 days time at our website is the deliverable 5.1, which shows it's a report about corrosion behavior of uncoated metallic materials inside the cell, where we present the behavior of this matrix of materials that you see in front under anodic and cathodic polarization in alkali and in seawater. And here just a few images to increase your attention to this deliverable that is coming up. You will find a lot of images, microscopy, and analysis by Raman, by profilometry, by interfacial contact resistance, how these metallic parts behave when they are subjected to polarization in seawater or in alkali. When we move to the second approach of electrolyzer configuration, as I mentioned before, we are having the reliable partner who is developing the hardware for electrolyzer and its propose. So within this approach, we are having the single cell hardware that is operating under hydraulic cell compression. This method gives us advantage of having all the active material being subjected to the same homogeneous pressure throughout the whole operation of the cell. Then we will be moving towards testing the developed materials in SWEETHY in the intermediate 5-cell prototype, which is almost ready, and this activity will be happening at RISE soon. And then you see the image of not real prototype, but this is the place for the final prototype, which is a 10-cell prototype of SWEETHY, which will be developed during the next year and will be delivered to CNR and tested until the end of the project with the novel materials developed in SWEETHY with seawater operation. So this approach will also pay attention to the byproduct analysis because we will have a lot of brine, heat, oxygen, precipitates that are formed during the electrolysis operation. And it is not good to waste even byproducts because they could be valuable products for other industries. So that is a very important part in SWEETHY Project that we are taking care of. And the last approach, sustainability analysis. As I briefly mentioned before, and I will tell more now, that we are exploring the stakeholder perspectives regarding the seawater electrolysis, and we map the options of integrating the SWEETHY electrolyzer into other industrial systems. We are looking at the sustainability analysis and how we can support the eco-design of SWEETHY electrolyzer in the end. Then we are developing how we will integrate the SWEETHY electrolyzer with the renewable power and with other industries. And of course, we estimate the cost. So far, 2 deliverables can be found at our website, which are concerning the sustainability analysis. The one is sensitive, so you are not able to access information, but it's about the stakeholder analysis, where we spread the questionnaire to some stakeholders to understand the potential technical, environmental, economical, and social risks and possibilities for the symbiotic solutions of SWEETHY towards other systems. However, another deliverable public one, D102, it is a screening LCA. So it's the first stage towards the full LCA that will be done during the later years of this project, is where we assess the CO2 footprint of the PGM and PGM-free stacks. So you're welcome to see these deliverables on our website. So all that I discussed before, I put in the timeline here. As you see, 4 years of the project, and we divided our project into 11 work packages, where the first 2 work packages are about project management and dissemination, communication, exploitation. That's why they are going through the whole timeline of the project. Then we have work packages 3, 4, and 5, which concern the development of materials and components, electrocatalyst in work package 3, membranes and ionomer in work package 4, anti-corrosion coatings in work package 5. Then we are assembling all the developed materials in the membrane electron assembly in work package 6, and we are doing the testing in the single cell. In work package 7, we are working also on the single cell level testing, but we are upgrading the testing of the SWEETHY materials in a 5-cell intermediate stack. In work package 8, we are designing the final SWEETHY prototype, which is a 10-cell, 120 centimeter square effective area stack. In work package 9, we're integrating this final prototype with a balance of plant at Sicily, and we are doing the long-term testing. And in work packages 10 and 11, we are assessing the sustainability. That's why these work packages are also stretched throughout the whole project line. Up to now, we reached 2 milestones. The first one is about formation of the advisory board, which are 5 stakeholders from different countries. We have the milestone 2, which was about harmonizing of the single cell protocols so that all the partners within the consortium are working at the same conditions on a single cell level when they are testing their newly developed materials. By the end of August this year, we have quite many milestones, 4 that we need to reach, and they're all regarded development and validation of the new materials that we are working on in SWEETHY. And they are also about completion of development of the intermediate stack, the hardware. in autumn this year, we'll also need to decide which materials will be chosen to implement in the final prototype. Next year, in August, we need to reach the milestone of when we characterize fully the novel materials on a single cell level, we optimize all the conditions, and we confirm that they are ready to be analyzed in the final prototype. And at the same time, we are ready with the hardware and integration of the final prototype. By the end of the project, of course, we need to complete the seawater direct testing on the final prototype of the newly developed materials. And what is very important for everyone is that we will organize the final event, which is, so stay tuned. We will announce that on the website as well towards the end of the project. And so within this half an hour, I hope that I could tell you more explicitly about what SWEETHY is. It is about, of course, the development of the novel and challenging technology, seawater electrolysis. But it is also about people and how we collaborate. This is a very important part of this multinational project where there are a lot of questions that need to, in the end, come to the good description, and they need to match to each other. So I want to show two pictures taken from the General Assembly meetings, one on the kickoff in Sweden in March 2025, and another one recently taken in France, where we had a meeting in Brest at the location of the French Corrosion Institute. But what else? It's about inter-project collaborations. So we are very thankful for this opportunity to have sister projects, as we call them, ASTERISK, HYSIS, and CIFA-Volt, which were financed by the same program within the same year. I also want to mention ANML, because we have a tight collaboration with ANML, mainly because this was the first project that gave the push for the seawater electrolysis technology to be under strong attention. And this is my last slide, where I would like to thank to everyone for their attention, and to thank to the partners, but also to the funding organizations, Clean Hydrogen Partnership and the European Union, who gave the possibility to have this project and these projects ongoing. Thank you.
Thank you so much, Olesia, for a very, very nice presentation. I like how you really delve deep into the science, and actually, we've got some questions coming up on YouTube about that. But before we move on to those, I just want to do a quick update for those of you who are not familiar with ANML, because we've mentioned it a couple of times during the presentation. So ANML was a project funded by the European Innovation Council in the Pathfinder Challenge scheme, in a call from, I think, 2021 or 2022, which is about to finish later this year at the end of 2026, and was in charge of developing anion exchange membranes for seawater electrolysis at lower TRL between 1 and 3 or 4. And now the same consortium continued along with ASTERISK, which is creating more sort of industrial technologies and technology transfer towards higher TRS, thanks to the funding of the Clean Hydrogen Partnership. And like I said at the beginning, this call from the Clean Hydrogen Partnership is also funding other projects like SWEETHY, working together with ASTERISK to develop cool technologies and new technologies that can actually become pilots in the area of direct seawater electrolysis. After giving the context on this, I just have like a sort of small curiosity, because we've asked all of the other projects presenting, why do you choose your water source in Sicily? I think it was in your case, and why does it matter to test different seawater sources? Is it the salts concentration? Is it the different ions? Is it the pH? Is that gonna be a important determinant in how the device works?
Yeah, surely. So seawater is different in different locations. this question I will divide into several answers, because you asked why we use water from Sicily. Mainly it's related to the fact that the final prototype will be standing there in Sicily, in the location of our partner CNR. That's why the water will be taken from there. But nevertheless, we are doing we will develop the case studies. It's not sure yet where exactly, but there are several suggestions. One suggestion that we will develop the case study for French coast, because we also have the partner there who is doing the corrosion testing. Then it could be also the case for Sweden. This will be known a bit later. But yes, seawater is different. It has different salinity. It has different microbial fauna, I think. So all these parameters, of course, they will influence because the salts, when they are being mixed, and Paul Farah said a lot of times about this soup of ions, but also soup of all these contaminants, microbial and other, they will influence which precipitates are formed in which amount, and how they will block the active materials of the cell and stack, and how they will influence the corrosion of the metallic materials.
Mm-hmm. Yeah, that's a really good point. I think we were also looking at Mediterranean waters, but also because we are so close to the Irish coast, we're gonna test the seawater from Galway, which is probably gonna be very different. But that's very interesting to know why you're doing the test with Sicily water. I'm gonna go to the very technical question in the chat, who comes from Senkian Tia. If it's too technical or complicated, maybe feel free to suggest that they contact you through email or through your webpage, because they're asking about why the benchmark catalyst for the oxygen evolution reaction is not iridium oxide, and also why do you see a drop in the reaction performance when increasing the voltage. But I don't know if this is right in your partner's expertise, or is it some of the other partners?
Yes.
So feel free to direct that to whoever is best fit to answer.
Yeah, exactly. I think that to have um, the more developed discussion, it's better to contact our partners. So I would ask to send me this email and the questions, so that I can also resend this to the partners that can explain more about this part. Because it also depends on which catalyst we're. So please send me the
So
email, and then we'll
if they
connect with the
go
right
to your
partners.
webpage, sweetie.eu, that's sweetie with an H for hydrogen, go there and you'll find the contact information. I think I see Juanjo typing. Someone gonna reply to you on YouTube chat with the instructions how to get back, and we'll direct you to the right person. I actually had like a question that is a little bit on the bigger picture area, wondering about the end users, because you've mentioned them briefly a couple of times during your presentation, and obviously we're trying to make green hydrogen mostly for hard to abate sectors. But if you had to choose one ideal end user for AEM electrolyzers, for seawater electrolysis, which one do you think makes more sense? Because I'm assuming something like mainland, like steel makers, maybe that's not a good idea. But are you thinking of a specific end user that could really benefit from the technology?
Are you referring only to anion exchange membrane technology, you mean, or seawater
I was
electrolysis?
thinking of an ion exchange membrane because it's
Mm.
ours, but in general, seawater is fine. Yeah.
I think when we are talking about the final user, they are not looking into which technology to use. They are looking into how much does it cost, and how they can couple to their byproducts. So you mentioned now the steel makers. Of course, when they are producing steel, they have a lot of heat. So if they can couple these industries, maybe it's interesting for them. But so that's why there is no answer for this question right now. The IM technology is not developed to say that they could be comparable to PEM or to alkaline. So I think that, as I said, the final customer, they will look not on the which type of technology to use, but they will couple it to the cost, efficiency, and to um, how they can connect to their byproducts, for example. That what drive them
Hmm.
most.
Yeah, I think
So I don't have an
eventually
answer for this.
it's no, it's fine, but it is both a little bit sad, but then also encouraging for the AM technologies that cost gonna be the final driver. So if we
Yep.
reduce the reliance on expensive materials, and make the technology very easy to sustain with cheap electricity like wind, and solar, hopefully we'll have a competing price to gray hydrogen and other technologies. So that's very good. I don't know if you've got anything else to add, Olesia, because for the sort of sake of time, I wanted to potentially bring this to a close. We're not getting any more questions from the chat. Anything else you want to add on behalf of Sweetie?
I just want to add that if there are questions arising, so everyone again is very welcome to contact me, and then I will try to connect to the needed people in the consortium who can give the more specific technical answers if needed.
Yeah, I think we added all the contact information in the chat, but just in case, sweetie.eu, you have all the information there. They do have a fantastic webpage and a cool newsletter, but so do we at Asterisk. So feel free to check our webpage, which I think it's somewhere around here, but I'm very bad at YouTube. So you should probably check that out as well and check out our social media. Both Sweetie and Asterisk are funded by the Clean Hydrogen Partnership and the European Union. We're very thankful for their support. And before we close, I just want to direct everybody to the symposium that Olesia announced at the beginning of her presentation. It's going to be a very interesting symposium in Sweden, in Stockholm, I think it's mid-October. So check out the webpage. Make sure that you subscribe to get all the information. I know that representatives from both projects are going to be there, from Asterisk and Sweetie, and also Animal. So if you're gonna be around, it's a very interesting symposium on the topic. Make sure that you subscribe to that. Looking forward to seeing you there in person, Olesia. Thank you again for a very nice presentation. And yeah, looking forward to more collaborations between Sweetie and Asterisk and the rest of the Seawater team. Thank you. Thank you so much for your time.